Okay. Morning, guys. Let me. Still no, huh? Even after cleaning it? That's disappointing. What about? Oh, hey, that's closer. There it is. All right, good. All right. Sorry, I'm fiddling around with this new keyboard. It's a wireless keyboard that I've had like sitting in my closet for a few months because my keyboard from Santa Fe died. It seems like when it rains, it really pours regarding these technology failures. But we're in good shape. I'm going to go ahead and connect the dot cam here, and we're going to get started. So, of course, this is Calc 2. Section 1. And today's the 12th of October. So, exam 1. Some of you should already see your grades, and some of you may not. So I've almost finished grading them, but I have not graded all of them. But those should be done today. Unfortunately, that drawing pad that I got from the college so that I could, oh, come on. The drawing pad that I got from the college so I could annotate your materials directly, not working very well. The thing is a mess. So we're going to, yeah, more broken stuff, yep. So last week, the network adapter in my main office computer died and I had to go get the machine replaced. And this week the peripherals broke. So the keyboard and mouse. So I swapped it out for a Logitech unit I had sitting in my closet. But also you may remember me bitching about that drawing pad. The drawing pad isn't broken, it just sucks. So I'm typing comments rather than being able to like draw them over things, and that takes a little bit longer. So I'll ask you to be patient with me. I'll get the rest of the grades in today. And that's always my rule, within a week. So then any other announcement-y things? Yeah, let me see. So I will be out of town. Well, no, we'll do that later. We'll do that later. All right. So then today, we're going to talk more about section 7.8 on improper integrals. And then we're going to introduce sequences. So you may remember that last week last Friday specifically, we wanted to talk a little bit about some theorems relating to the convergence of improper integrals, some tools that would allow us to tell when those things converged, even if we didn't necessarily know the value of the integral, even if you couldn't do the antiderivative step. That's the idea. So that antiderivative step can be a real pain in the ass sometimes. It's not always manageable. And there are a handful of very important integrals that I would still like to know the convergence question, but I don't necessarily expect to be able to find the value. So we're going to address two major theorems there. And I showed you one of them last week, but I want to kind of revisit the whole thing. There's one other announcement. Homework has been extended. Because we didn't get to talk about those theorems last week, I'm extending homework 6 to Wednesday. I got an email from one of my students who was nervous about this, and I went ahead and already did the extension. So yeah, it's been pushed to Wednesday, the 14th. Okay. So two important theorems. On convergence of improper integrals. Before I show you these theorems, I want to drop a little introduction to this part of the class. I know I did something like this last week, but just bear with me. So remember, this class is sort of split up into thirds. The beginning third is all about integration. The middle third is all about convergence. And the latter third is all about applications. We're entering the middle third, right? This improper integral stuff is the first place where we've been dealing with the questions of convergence. And specifically what we're doing today is kind of the start of us addressing that in the way that we will address it for the remainder of this middle third. Meaning, rather than attacking most of these things directly, whether they're series, sequences, or improper integrals, most of the time we will attack them indirectly using theorems like the two I'm about to show you. What that means is that you need to have a strong control over the theorems. You need to know the hypotheses, all the stuff that comes after the word if and before the word then. And you need to know the conclusions, all the stuff that comes after the word then. You need to know them exactly, right? So think of theorems as mathematical tools, right? Like hammers. You need to know how to hold the hammer, how to swing the hammer, and how to hit the nail. So you need to know what the theorems are and where they, what things they apply. And you need to know how to use them. And that means knowing the hypotheses and knowing the conclusions exactly. The way to get there is to make use of them a lot, right? I could talk about hammers all day and say like, oh, well, this is a nail. This is how you hit the nail. The hammer is the thing that you use to hit the nail. But you're not going to be able to get a nail into a board without bending it unless you spend a lot of time actually practicing. The same is true of these theorems. So make sure that you practice them until you know them. My other comment is you should have dedicate three whole blank pages in your notes for convergence tests. And I would take them outside the normal flow of your notes, right? So I wouldn't put them all, like if you're working in a notebook and you just start a new page every day or whatever, I wouldn't put those 3 pages like right here, wherever it is that you are in your notes. I wouldn't save them right here. I would like flip to the back of the notebook and cordon off 3 pages there or something like that. Because these theorems are kind of lengthy and you'll want to have somewhere you can flip to them quickly and find them so you can refer back to them because you will be doing so often. So I'll say that again. Right now, in your notebook where you're taking notes, flip to the back and mark off 3 pages for convergence tests. 1 page for improper integrals, 1 page for sequences, and 1 page for series. You may even want like 2 pages or 1.5 pages for series because we have quite a few tests there. Okay. You've been warned. Class is changing gears. You're going to need to learn how to work with theorems. It's a new thing. So even if you've been doing well, come back to that humble state of not really knowing and acknowledging that and being ready to practice. The theorems, there's several of them. And I think I would like to start with the theorem on P integrals. So we've seen that the integral from 1 to infinity of 1 over x dx diverges and the theorem, the integral from 1 to infinity of 1 over x squared dx converges. The graph of 1 over x in that first quadrant looks like this. And the graph of 1 over x squared in that first quadrant looks very similar, except it kind of sits down a little bit harder than this guy. He's like if you take this guy and go and squish him down a little bit, you get this guy. So the area on the left over there is infinite, and the area that I just drew here is finite. And the question is why? Zach, yeah, the stuff that I'm introducing now is stuff that will go into your integral section. So for now, right, what I'm doing right here, write your notes as you normally would. But then when we finish today, take the 2 theorems I'm about to show you and add them to the improper integral page in the back of your notebook, right? Does that make sense? So take notes like normal today, but then when you're done, take the 2 theorems that I'm showing you and add them to this special page in the back of your notebook. So what I'm doing right now is introducing the first of the 2 theorems that we're going to have from section 7.8. So the question is, what is it about 1 over x squared that allows his integral to converge while the integral of 1 over x diverges? And what other sort of integrals could we look at? So here's the theorem. I kind of already gave it away here, right? It's the fact that this guy sits down so much harder on the x-axis than this guy that allows this area to be small enough that even though it goes on and on and on forever to the right, it's still a finite area. The theorem is called the result on P integrals. And I believe this should make sense given the examples we've seen. First, integrals. So for now, take notes like normal, right? And then when we're done, take this theorem and put it in that integral page in the back of your notes. Integrals of the form integral a to infinity of 1 over x to the p dx, where a is a positive number, are called P integrals. And the result says that P integrals converge if P is bigger than 1 and diverge if P is less than or equal to 1. So functions of the form 1 over x to the p all have the same basic shape to their graph, at least in quadrant 1. And the larger p is, the faster they settle down on that horizontal asymptote y equals 0. So if p is small, then they'll settle down slowly. If p is large, then they'll settle down fast. And that settling down fast, that going to 0 fast, is what's necessary for these integrals to converge. I'm going to prove the result for you. Mathematical proofs are usually a little bit terse and a little bit hard to read. But this is what mathematicians actually do. A lot of people think mathematicians spend their time doing calculations, when in truth, what we do is we spend our time proving theorems. We consider 3 different cases. So I'm telling you that the convergence of these integrals depends on P. P being less than, consider 3 different cases. P being less than 1, P being equal to 1, and P being bigger than, I keep writing 0, 1. It is, yeah, it's a mind-blowing fact that you can have something that's infinitely long but have finite area. This took a long time for me to even become comfortable with when I was in Calc 2. And it should be shocking, right? I agree with Nick's statement in chat there that this is fairly shocking in general, that improper integrals of either type can converge, but it is true. And the basic idea is that in type 1 integrals, for example, that the height needs to get small very, very fast in order for the overall area to be finite, because the width is infinite. So if the height doesn't get small, then there's no chance for the area to be finite. And it turns out, like with 1 over x, where the height does get small, it just doesn't get small enough fast enough. So not only does the height need to get small, it needs to get small really fast in order for the integral to converge. All right, we consider 3 cases. If P is less than 1, then the integral from a to infinity of 1 over x to the p dx, I just compute the integral as the limit. So r goes to positive infinity, integral a to r of x to the negative p dx. My antiderivative looks like this. It's x to the negative p plus 1 over negative p plus 1 evaluated from 1 to r. And the important thing here is that we think about this power. If p is less than 1, then is negative p plus 1 bigger than 0 or smaller than 0? I'll pop the constant term out. I've got a 1 over 1 minus p that can come out. So this is 1 over 1 minus p lim r to infinity. And then inside here, I have, oh, and this should be an a, sorry, not a 1. Then I'll have r to the negative p plus 1 minus a to the negative p plus 1. And I'm sending r to infinity. So the piece I need to think about is this. And the limit here is going to depend on whether this power is positive or negative. If the power negative p plus 1 is negative, then this r term really belongs downstairs. And as r goes to infinity, that term will go to 0. If the power negative p plus 1 is positive, then this r term really belongs upstairs. And as r goes to infinity, it will go to infinity. So I ask you, if p is less than 1, is negative p plus 1 positive or negative? Good, right? The p piece here is negative, And if p is small, then the 1 will win, right? Think about an example where p is less than 1. If p is 0, then negative p plus 1 is positive. If p is 1/2, then negative p plus 1 is positive. So then what is the limit as r goes to infinity of r to the negative p plus 1 if this power is positive? What happens to positive power functions when you send their variable to infinity? If you're having trouble with answering that, think about a specific example. If p is 0, then r to the negative p plus 1 is just r to the 1. If p is 1/2, then r to the negative p plus 1 is the square root of r. Yeah, if p is less than 1, then this limit is infinity. So my integral a to infinity 1 over x to the p dx is equal to the limit as r goes to infinity. I've got a factor of 1 over 1 minus p that I'll slap on at the end. R to the negative p plus 1 minus a to the negative p plus 1 times 1 over 1 minus p is infinity. Because this piece is going to infinity and everything else is finite. So the integral diverges. And we were expecting that because that's what the theorem said. It said that the theorem would converge if p is bigger than 1 and diverge if p is less than or equal to 1. And what we've just shown is that if p is strictly less than 1, the integral diverges. Okay, the next case we're going to handle is if p is equal to 1, then the integral from a to infinity 1 over x to the p dx is the integral from a to infinity 1 over x dx, which is lim r to infinity integral a to r 1 over x dx, which is a natural log. This is lim r to infinity natural log of r minus natural log of a. And this one's easy. In fact, we've already done this just in the special case where a is equal to 1. Since lim r to infinity natural log of r is equal to infinity. Remember, this is a limit I reminded you guys of last week. It's an important limit. The natural log function goes to infinity slowly, but it does go to infinity. Since this is infinity, the integral from a to infinity 1 over x dx equals infinity. So the integral diverges. And then the last case to handle is if p is bigger than 1. All right, so if p is less than 1, the integral diverges. If p is equal to 1, the integral diverges because this limit is infinity minus the natural log of a. Natural log of a is finite. Infinity minus something finite is always infinity. So the integral diverges. If p is bigger than 1, then the first few steps look the same as in this first case we dealt with. Then the integral a to infinity 1 over x to the p dx is equal to the limit as r goes to infinity. I'm going to skip over these first few steps here because we know what these look like. It's exactly the same. So this would be 1 over 1 minus p times r to the negative p plus 1 minus a to the negative p plus 1. Because again, if p is bigger than 1, then it's a power rule integral the same way as if p is less than 1. The difference here is that now since p is bigger than 1, the power negative p plus 1 is negative, right? If p is bigger than 1, then negative p plus 1 is negative because the p part is bigger than the 1 part, and he's negative. Like negative 2 plus 1, negative 3 plus 1, negative 3 halves plus 1, negative 10 plus 1, all of those are negative. So the r term here really belongs downstairs. And limit r to infinity, r to the negative p plus 1 minus a to the negative p plus 1 is equal to, what does this piece do as r goes to infinity if this power is negative? Like 1 over r squared, 1 over r cubed, what do those do as r goes to infinity? Good. Goes to 0. So this is 0 minus a to the negative p plus 1. Which means the integral from a to infinity 1 over x to the p dx is equal to 1 over 1 minus p times 0 minus a to the negative p plus 1 converges. And that's it, ladies and gentlemen. That's the result on p integrals. If p is less than 1, you can compute the integral and discover that it diverges. If p is equal to 1, you can compute the integral and discover that the integral diverges. And if p is greater than 1, then the integral can be computed and discovered to converge. So p integrals converge if and only if p is larger than 1. And that is the theorem. That was what we wanted to prove. You're not responsible for the proof itself. You are responsible for knowing the theorem. So a quick comment. P integrals are always type 1 integrals. So to apply the result of the theorem on P integrals, you must be working with a P integral. That means the integrand first must be type 1. and the integrand can only be 1 over x to the p. So don't try to apply the p theorem or the theorem on p integrals to anything other than p integrals. Sine x over x squared dx from 1 to infinity is not a p integral. Even though the thing has a 1 over x squared in it, the sine x upstairs ruins the p integral. It's not a p integral if there's anything other than 1 over x to the p inside. The integral from 2 to infinity of 1 over x cubed dx, this is a p integral. Integral 1 to infinity 5 over x squared dx is not a p integral, but it is a constant multiple of the p integral integral 1 to infinity 1 over x squared dx. And then finally, integral -2 to infinity 1 over x to the 4 dx is not a p integral. Okay, so why is the first one not a p integral? Remind me, what is it that makes this thing not a p integral? Good. It's not, the integrand isn't the right shape. It's not just 1 over x to the p. The sine x upstairs ruins it. The joke I tell to help this stick in our mind is that anything other than 1 over x to the p ruins the p-ness of the integral. I know. Okay, the second one is a p integral because it's a type 1 integral, and the integrand is just of the form 1 over x to some power. The third guy is not a p integral, but it is a constant multiple of a p integral. So you could pop out the 5 and then apply the theorem to this guy. And obviously, if this guy converges, then 5 times him will converge as well, right? Because if you're finite, 5 times you is finite as well. Why is the fourth example here not a p integral? Good. What about the bounds? Yeah, a is not positive here. In fact, this isn't even a type 1 integral, is it? It's got type 1 and type 2 stuff, because the function 1 over x to the 4 has an infinite discontinuity at x equals 0. And when you integrate from -2 to infinity, you're jumping over that infinite discontinuity. So remember, p integrals are always type 1 and just type 1. Okay, so those are p integrals. Which of these do you think converge? Let's call them integrals 1, 2, 3, and 4. I'll take votes on integral 1. This isn't a p integral, but does anybody have a guess as to whether or not this converges? So Nicholas thinks it converges. Does anybody else agree or disagree? Yeah, that feeling in your bones is a good feeling. This is a convergent integral. The 1 over x squared that's in there is dragging this thing down. In fact, if you look at the graph of sine x over x squared, let's do that real quick. Oh, type. And let me rescale my y-axes. So x's, let's send these out as far as we can. Y-axes, let's scale these way, way back. Desmos might be shitting the bed here. That's a little too much to ask for, huh? Okay, and then let's get way in there on the y's. Here we go. So this is the graph of sine x over x squared. We don't need to go out as far on the x's. Let's just go to 50. Here we go. And what you'll see is that this is kind of trapped underneath 1 over x squared. He's not always positive though. So the integral of the red function, you might worry that some of this negative stuff is going to get you in trouble. But because he's trapped underneath 1 over x squared, and we know 1 over x squared to converge, we've got good reason to expect that the integral of sine x over x squared will converge as well. And I'll give you a theorem that helps you discover that next. Yeah, yep. Okay. Converge or diverge? Integral 2. Yeah, this is a convergent p integral. Here p is equal to 3. 3 is bigger than 1. So he converges. Converge or diverge? Yeah, integral 3 also converges. He's not a p integral, but he is a constant multiple of a p integral. And the p integral that he is a constant multiple of has p equal to 2, which again is bigger than 1. Integral 4. So I'll go ahead and recap what we have here. We think this guy probably converges. This one definitely converges. This one definitely converges. So what about this guy? So on the fourth integral, the type 1 piece, the piece that goes from 1 to infinity, right? If you split this integral up as the integral from -2 to 0, let's see. So let me make sure we remember how to handle this, and this will be a good last thing to do here. So for the fourth integral, we would treat it as integral -2 to 0, 1 over x to the 4 dx, plus the integral from, say, 0 to 1, 1 over x to the 4 dx, plus the integral from 1 to infinity, 1 over x to the 4 dx. We talked about how you would handle these last Friday, because you've got type 2 issues at 0, and because 0 is in the middle here, you're going to end up with two integrals from that, one on either side. The picture here looking like this. We want to integrate from -2 over this problem spot at 0, and then all the way off to infinity on the right. So we have to split it. Right, we do the integral -2 to 0 to take care of this danger spot. We do the integral 0 to 1 to take care of this danger spot, and then we do the integral 1 to infinity all separately. This guy certainly converges, because he's a p integral with p equal to 4, which is bigger than 1. So the type 1 portion of this is a p integral. The problem is just that this integral has mixed type 1 and type 2 stuff. The two type 2 portions, these guys, anybody got a feeling for whether they converge or diverge? If you did your homework, you would have an answer for this. There is a homework problem that would allow you to at least resolve the middle guy here. Remember the question, for what values of p does the integral 0 to 1, 1 over x to the p converge? Well, for those who haven't done that problem, this will serve as a hint. These both diverge. They're not p integrals because they're type 2. But if you do the computation, you'll discover that both of those diverge. And in fact, the rule for type 2 integrals that kind of look like p integrals, i.e. have the same shape to the integrand, are exactly the opposite for type 1 p integrals. So this guy, he's going to end up diverging. Because if any part of the integral diverges, the whole integral diverges. Remember that from last week? Both of these parts diverge. So even though this piece converges, the whole thing diverges. Okay. I have another theorem for you. This is called the comparison theorem for improper integrals. So again, put this in your regular notes now, but then after class, go back and add this and the theorem on p integrals to your special little convergence section in your notes. These are the two main theorems from section 7.8. This says if 0 is less than or equal to f of x is less than or equal to g of x on the interval a to infinity and integral a to infinity g of x dx converges, then integral a to infinity f of x dx converges. That's 1. And 2, if the integral from a to infinity of f of x dx diverges, then the integral from a to infinity of g of x dx diverges. So a simpler way to say this is, if u are smaller than a function whose integral converges, then your integral converges, right? If the integral of the big guy is convergent, then the integral of the smaller guy must also be convergent. Or another way to say this is, if you fit in a finite box, you must be finite in size, right? The area being measured by f of x fits inside the area being measured by the integral of g of x because f is smaller than g. So maybe here, this is, the blue is f of x, and the black is g of x. And if a is here, then the blue area is contained in the blue area is contained in the black area. So if the black area is finite, then the blue area is finite. And if the blue area is infinite, then the black area is infinite. Make sense? So if you fit in a finite box, you've got to be finite. And also, if an infinite box fits inside you, then you have to be infinite. Or you can think of it as, if the integral of the bigger guy converges, then the integral of the smaller guy converges. And if the integral of the smaller guy diverges, then the integral of the bigger guy must diverge. This theorem is very similar to a couple of theorems we're going to learn about series. And so this theorem especially, you need to get comfortable with. The theorem on p integrals is not too hard to get comfy with. It's just a matter of remembering. This guy is something that has a little bit of conceptual depth, and you want to make sure you understand it all the way. Are there any questions about what the theorem is saying? A quick note before we move on is that the positivity requirement is important. The 0 on the left-hand side, you need to make sure that this is true as well as this. So make sure you can only apply this theorem to positive functions. But for positive functions, it works great. And there are a few problems like this in your homework. So for example, I could ask you to investigate the convergence of the integral from 1 to infinity sine squared x over x cubed dx. Are we all done writing down the theorem? Can I remove this page? Any no's on that? Okay. So I want to know whether the integral from 1 to infinity of sine x squared over x cubed converges or diverges, right? Investigate the convergence. Tell me whether it converges or diverges. Unfortunately, you will not have any luck attacking this directly. Finding an antiderivative for this function is extremely hard. I don't mean hard like difficult Calc 2 problem, I mean hard like no mathematician in the world can do it without using infinite expressions. So instead, we're going to need to attack indirectly using one of our theorems. So I'm going to attempt to use the comparison theorem. Because this is not a p-integral. The whole sine squared thing upstairs ruins the p-ness of this integral, right? It is not a p-type integrand. But I can compare it to something. What would be a good thing to try and compare this integral to? I think we can do better. Yeah, 1 over x cubed, right? 1 over x cubed. So there's two things you want to keep in mind for your comparison. The inequality, and then how difficult is the integral you're wanting to compare against to evaluate. You want the integral that you're comparing against to be as simple as possible. And then, of course, you need your inequality to be true. So first, I'm going to build the inequality. My aim is to compare with the integral 1 to infinity 1 over x cubed dx. So we know that sine itself, sine x, is always trapped between -1 and 1. And this implies that sine squared is always trapped between 0 and 1. Right? If you take a bunch of things that are between -1 and 1 and you square all of them, the result will be a bunch of things between 0 and 1. This implies that 0 is less than or equal to sine squared x over x cubed is less than or equal to 1 over x cubed. So this process of building up your inequality from things that we know Very important process. Again, not just for this section, but also for the similar sections relating to series. So building inequalities is a skill that we need to learn. Are there any questions about how I arrived at the third inequality or what we did to get there? Where we began? Any of the steps? Which part feels weird? So to go from the second to the third, I just divided every term by x cubed. Since I'm considering x's which are bigger than 1, x cubed is positive. So when I multiply or divide by him, he doesn't mess up my inequality. And since I have this line as something I know to be true, I can divide everywhere here by the positive quantity x cubed and get another statement which I know to be true. I've just written 0 over x cubed as 0 because that is still 0. Now what I would do is I would give this last inequality a name. I would call it star and say the integral integral 1 to infinity 1 over x cubed dx is a p integral with p equal to 3. So it must converge. Thus, by the inequality star and comparison theorem, for improper integrals, the integral from 1 to infinity sine squared x over x cubed dx must also converge. And as you write out these problems, the words matter at least as much as the calculation. You notice there's very little calculation going on here. This is like a logic puzzle. I don't really give a shit about calculation in this middle third of the course. There's very little calculation going on. There's going to be a lot of inequality building and a lot of writing, like a lot of words. It's super duper important that your logic is sound. And this is a place where it's possible to get things really badly wrong without knowing it. So you need to do yourselves and honestly me the favor of sharing your work with other people before the test. I would say right away. I don't know if you guys have a Discord or a group me for this class. Has anybody started one of those yet? You can be honest. I'm not going to force intrude upon any of them. I just want to know if one exists. It's a good thing. If there isn't one, I'll start one. No? Okay. I'm going to make a note here to start a Discord for this class. And I'll post the link in Canvas. So use that as a place where you can share your work with each other, right? If you're having trouble with a problem, post and your classmates can help you. If you have a solution that you like, post it and show it to your classmates. If you have a solution that you're not sure of, post it and share it with your classmates and make a point of discussing with one another to make sure that your logic makes sense, make sure that you agree with each other. Try to fight with each other about this shit. This is one of the things that's fun about being a mathematician. What mathematicians do is we sit down, we drink a shitload of coffee, and we call each other stupid, basically. We sit down, not literally, but we sit down and say, no, I think your argument is all fucked up. It doesn't make any sense. There's this wrong with it. There's that wrong with it. And through this process of trying to discover what's wrong with something, you end up making a perfect argument. And those are called proofs. What you guys are doing here is learning how to write proofs. Right? Each one of these problems where you have to say that something converges or diverges is essentially a proof. And you need to be practicing that. So it would be really helpful if you had this experience and a place to argue with each other. So please do so. All right, that's enough time on this stuff. I think especially given the practice that we put into this stuff last week, I feel comfortable moving away from section 7.8 now. So in these last few minutes of class, what I would like to do is to introduce sequences, which is the material that we're going to be spending the rest of this week on. And it's sort of the building block for all of the other convergent stuff we're gonna do. So before I leave 7.8 entirely, are there any other questions on improper integrals? Yeah, I'm wrapping them up. So you guys, your grades, if your grade isn't in yet, it'll be in by the end of the day. Okay, any other questions on improper integrals? Okay. So the class takes a big jump here in terms of section numbers. We move all the way to chapter 11. And the new homework that's going to be opening up this week is going to have section 11.1 in it. Section 11.1 is all about sequences. Hopefully you are exposed to sequences in your pre-calculus class, but I understand that not every pre-calculus class covers this stuff, even though they're supposed to. And even if your pre-calc class did cover it, it would have been a little while ago, so there's room to forget. So I'm going to begin with a definition. And there's more than one correct definition for sequences. So first, a sequence is an ordered list of objects. Usually the objects are numbers. But you could, in theory, have a sequence of cars, a sequence of planes, a sequence of concepts, a sequence of anything. But for us, it's an ordered list of numbers. So there's like a first term in the sequence, a second term in the sequence, a third term in the sequence, fourth term in the sequence, fifth term in the sequence. So this is an example of a sequence. The notation looks like this. So I read this as A1 or A sub 1. We wouldn't say A to the 1. It's not a power. It's an index. So this is A1. This is A2. This is A3, A4, and A5. A1 is the first term of the sequence. A1 is 3. A2 is the second term of the sequence. A2 is 1. A3, the third term of the sequence, is 4. A4, the fourth term of the sequence, is 1. And then I think I fucked up here because I intended to use the digits of pi, but I should have had a 9 here. A5, the fifth term of the sequence, here would be 5. In general, the nth term of a sequence is written as an, which we read, or which is pronounced How do I do this? How can I write this out phonetically? Just an, right? For whatever reason, especially in pre-calculus, people get in the habit of pronouncing this as a to the n, which is confusing, right? Because it's not a power. And a itself is not a number. So that pronunciation or that phraseology doesn't really make sense. You could call it a sub n if you want, or even a of n. But please not a to the n. That will be really confusing. Another way to define a sequence, if you think about what this does, is as a function. Over here, this says the first term of the sequence is 3. So I could think of the second term of the sequence is 1, the third term of the sequence is 4, etc. I could think of this as a function that takes the indices here, these numbers, and sends 1 to 3, sends 2 to 1, sends 3 to 4, sends 4 to 1, sends 5 to 5. So another definition is a sequence is a function whose domain is the natural numbers. Instead of writing like f of n like this, we write a sub n like that, but that's the only difference, is the notation. Sequences can be given a bunch of different ways. One of the ways to describe a sequence is to just list off the first few terms and expect your reader to deduce the pattern. And that's valid as long as there is a unique pattern that can be deduced from those first few terms. When we do that, we usually put the terms in curly braces. So I could ask you to find a formula for the sequence an whose first few terms are maybe 1, 1/2, 1/3, 1/4, 1/5, and so on. Does anybody see a pattern here? Yeah, what would the next term of the sequence be? And after that would be 1/7, and after that would be 1/8. Zach, there's actually more than one way to write this. So what I really should say is I should also specify the starting value of n. So if n starts at 1, then I would say an here is just 1 over n. If n started at 0, then I would say an is 1 over n plus 1, as Zach wrote it. And you're often free to choose, unless the problem tells you. But if you're working with sequences on your own outside the context of a specific problem, you can choose whether the sequence starts at 1 or at 2 or at 3, whether you want to call the first term A1 or whether you want to call the first term A0. The set of the natural numbers that is supposed to be the domain of these sequences, some people include 0 as a natural number and some people don't. Personally, I do include 0 as a natural number, but your textbook doesn't. So in my examples, where convenient, I will go with the textbook's notation, which is that these sequences usually start at n equals 1, but sometimes it just makes things a little bit unpleasant. So yeah, Zach, your answer would be fine if n started at 0. But if n started at 1, as it usually will in our homework problems and in our textbook, then I would just say here an is 1 over n. Okay, let's try something a little more complicated. Same thing, find a formula for the sequence an whose first few terms are, let's say, -1, +1, -1, +1, -1, +1, -1, +1. What would be the next term in this sequence? Does anybody see a pattern here? Yeah, the next term would be -1. And then after that, +1. And then after that, -1. And then after that, +1. Can anybody think of a formula that outputs those sort of numbers? -1 to the n. Yeah, Zach's getting clever there with trig functions. There are a couple other answers to this problem. So I would argue that the most natural way to write this is as -1 to the n. Now, sine of pi over 2 plus n doesn't quite work, but there's a couple things like that which do. And I'll show you those as well. So first, the most natural way to do this is -1 to the n, right? -1 to the 1 is -1. -1 squared is +1. -1 cubed is -1. -1 to the 4 is +1 again. So the most natural way to do this is as -1 to the n, but you are correct in saying or thinking that this could be done with trig functions as well. The easiest way to do it with trig functions is as the cosine of n pi. Because cos of 1 pi is -1, cos of 2 pi is +1, cos of 3 pi is -1, and so on. All right, Nick. Another way to do this with the sine function, I gotta think about this for a minute. We need to land at the odd multiples of pi over 2. So that would be the sine of 2n plus 1 times pi over 2. So that's like sine of pi over 2, which is 1. Oh, wait, hang on. Yeah, this almost works. Sine of 3 pi over 2, which is -1. Sine of 5 pi over 2 is +1. So this guy you would need to shift a little bit. He does the same sort of +1, -1, +1, -1 thing. But he starts at +1 rather than at -1. So if you made that like 2n - 1 instead of 2n + 1 inside here, this would fit exactly. But yeah, most natural way to do this is as -1 to the n. So if we are out of time, and we are, then we will pick it up here on Wednesday, right? So finding formulas, detecting patterns, this is sort of the first thing you need to be able to do with sequences. But the main thing we're going to be doing is taking limits of sequences. So we will have a new concept of convergence that we apply to sequences, separate from the concept of convergence for integrals. And we'll talk about some theorems that guarantee the convergence of a sequence. After we're comfy with sequences, we're going to introduce series, which are like integrals of sequences, really. That's the best way to think of a series. But it's going to be a little bit before we get to that. So for now, focus on wrapping up the 7.8 homework. I would like that to all be done by Wednesday. That is the new due date. Remember, homework 6 is now due at the start of class on Wednesday. So make sure you get that done. And then I will get homework 7 published for you guys today. And we'll continue talking about sequences in class on Wednesday. All right. Take care, guys. Have a lovely rest of your day. And if you want to talk more, you can come by office hours this afternoon.